Alrighty. Hello, everyone. Hi, Sai. My name's KJ. I work at Zendesk as a principal engineer, and I'm also now a committer on the Ruby core team. And I'm here today to talk to you about address sanitizer, also known as ASAN. I was a bit terrified that they put this speech in the big hall, because this is a pretty niche topic, but I'm glad that only a few people were interested, so thank you for coming. All right. Also, apologies in advance about, this has been a bit of a difficult topic to pitch at the right level, so if this all goes over your head, I'm sorry, and if this is really obvious to you, I'm also sorry, but hopefully there's something at least for everyone. Okay, so let me start by setting the frame about the problem that this talk is about. So I'm sure many of you have had the misfortune of seeing what it says up on that screen, the C Ruby crash dump. If you see that, it means Ruby has crashed. And that means there's either a bug in Ruby or a bug in a native extension gem that you're using, because Ruby code is never supposed to be able to crash the Ruby interpreter like that. So I started looking at ASAN and working on address sanitizer and getting it into Ruby in the hope that it could help with these sorts of crashes. So that's what this talk's about. So we'll start by kind of talking about ASAN, as a thing. What is it? Why do people use it? How it works? And then we'll shift gears a bit and talk about the work I did to get ASAN working in C Ruby and what we can do next with that. All right, so first question, what is the address sanitizer? So the C programming language has so many rules, right? Don't do any of the things in that list. Don't write past the end of buffers. You've got to make sure you manage all your memory correctly. And the compiler is a little bit helpful sometimes, but mostly not very helpful. You're on your own. If you do these things, what actually happens is you get undefined behavior, which can mean that absolutely nothing happens, everything is fine, or it can mean that your program crashes, or it can mean, most annoyingly, that your program works fine for a little bit and then crashes later. So the idea of ASAN is to be kind of a tough cop, a linter, or an enforcer, and it's supposed to enforce the rules much more strictly than C normally does. So it's a compiler flag. You just turn it on by passing fsanitize address to your when you use the C compiler. And what ASAN does is it makes your app crash the first time it breaks these rules. So instead of you break some of C's rules, and then at some later point, something very mysterious happens and your app crashes, you get the crash right away. So we can illustrate this with the world's worst hello world program that I wrote in C. So what this program does is try to copy 16 bytes of hello into 8 bytes of hello copy. And a 16-byte array doesn't fit in an 8-byte array. And so we have violated C's rules here. This is undefined behavior. However, the compiler will, after you ignore all the warnings, compile this. And if you run it, what happens is, obviously we get a segmentation fault. Our app crashed. But before it got there, it did actually print that big hello, because it successfully ran the string copy on, was that line 10? And then it then went to the next line and printed hello, and then when it went to print world, that's when it crashed. Even though there's nothing at all wrong with that line of code is correct. The bug was earlier. So, and the reason this happens is because C's kind of laid out all the variables together. So you've got the hello buffer next to the world pointer, but if you just write lots of hello, it kind of just overflows and goes into the next slot, and suddenly what's supposed to be a pointer contains a bunch of O's in it, and thus crashes. So the idea of ASAN is that this program is going to crash, but let's make it crash better. So if we compile this program with fsanitize address, what we see is it still crashes, but it crashes right there on line 10. You can see, you've got the backtrace of the crash. It also tells you, a bunch of interesting things, like what kind of memory rule you violated, the code that your program was executing, the stack trace, what variable you were trying to access. So this information is like infinitely more useful to debug the issue than that, right? And so, oops, that was backwards. Should have practiced that more. And so that's the point of ASAN. We want to make applications like the Ruby interpreter crash the first time they break the rules, rather than crashing at some later point in time. So where does ASAN fit into kind of the software development picture, right? Where is this useful? So ASAN adds around about, they say 2x overhead. I found sort of 5 times overhead when I have used it. So it's going to make applications way too slow to use in production. I don't think anyone is going to get away with compiling Ruby with ASAN enabled and then like serving their production Rails app with that. That would probably lead to some very upset customers who are waiting a long time for whatever they're doing. But this is fast enough, I think, to use it in development a lot of the time. And it's fast enough that it has a role to play in CI as well, in continuous integration testing. So in the development workflow, I'm sure some of us have written some code, and it worked on our machine most of the time where we tested it. We released it, and then some people used it, and then they opened an issue, and then we had to fix the issue from like it crashing on their computer. And this is slow and takes a long time, and it's nice if we're building with ASAN in development to be able to get crashes straight away rather than having to go through this whole cycle. So using ASAN in development can give feedback, basically, about errors that people were probably going to run into anyway later, but you get them now instead. It can also help with diagnosing like crash reports. So this is an issue that someone opened a few months ago, and he said that, OK, this particular program crashes the Ruby interpreter, and that's not supposed to happen. So there's a bug in Ruby here somewhere. And I was able to run the reproduction script with address sanitizer enabled, and that gave me a much more useful backtrace that pointed more clearly at the cause of the problem. So ASAN can also help, like reproducing issues that are reported. ASAN, I think, also has a role to play in continuous integration testing. So that's a screenshot of Chromium's CI runner build thing. They test with ASAN and a lot more besides, but they build Chrome with address sanitizer enabled and run all of Chrome's unit tests through that. And then you can check if a memory error is being introduced that's caught by a test suite, and we can not merge that thing or revert it straight away. So yeah, that's probably where ASAN fits in. It's a development tool, and it has a role to play in tests. OK, so that's what ASAN does and what we want to do with it. Let's have a look a little bit under the hood at how it works. So address sanitizer is a part of the compiler. That means it works by kind of modifying the generated machine code. So you might build a program with GCC, and you might build it with GCC with ASAN enabled, and those two programs will be very different in terms of what's in them. And they're different in a few ways. So there's it uses something called shadow memory to keep track of what memory is valid. It uses instrumentation to check against that shadow memory, and it puts red zones around objects. So we'll go through those things kind of one at a time at a really high level. I'm not really a compiler guy, so I might not be able to do this the best justice, but we'll see how we go. All right. So ASAN maintains, at runtime, this thing called shadow memory. And that means you've got kind of a complete map of what memory is valid at all times in the application. So your program might have some variables in memory, like this character string or this number that's on here. And in between those is empty space. The rules of C tell you that you can access the variables that have been allocated, but it's not valid to access the empty space between them. So ASAN basically maintains this shadow map of addresses that are valid and addresses that are not valid. And kind of end up, it uses 1/8 as much memory to literally maintain a copy of whether any given piece of memory is valid or not in this other region of memory. And the reason it does this is so that it can do instrumentation. So ASAN rewrites all of the memory access in your program. So normally, hello3 would look at the third character of the hello array and return that. But when ASAN is enabled, that turns into a two-step operation. First, it checks the shadow map to see if that's actually a valid thing to do. And if so, it will continue to then load the memory. But if not, it will crash the program. So this is kind of useful to see an example, perhaps. This is a function. It does some very obvious things, like set that value to 42. And if you look at what code the compiler generates normally, it's pretty straightforward as far as assembler goes. It's like 3 instructions to put 42 in there and return. Now, if you compile the same function with ASAN enabled, you get that monstrosity. And this is why ASAN makes your program 2 to 5 times slower. It's because every time you access memory, you have to do all of this extra machine code. And this is what implements the logic of checking against the shadow map. So that kind of gets inlined absolutely everywhere your program accesses memory, which is probably quite a lot of places. The other thing that ASAN does is put red zones between objects. So normally, C will often lay objects out next to each other. And if you remember from our previous hello world example, we had hello and world next to each other. So when we overflowed hello, it clobbered world. So ASAN avoids this by making sure to allocate kind of extra empty space around every object. So this picture is ASAN's map of the shadow memory that it prints out. And there's a valid object in there. And surrounding that valid object is bytes of memory that ASAN has allocated but are marked as invalid. So they're called red zones. So that means if you try to copy a big array into a small array, it'll hit the red zone at the end of the object before it can go any further and clobber real things. And once it hits the red zone, that's not a valid address. So all the instrumentation will notice, hey, I'm not allowed to write to the red zone, so it crashes. OK, so that was a big spiel about ASAN and what it does. Let's have a little bit of a look about what role it has to play in C Ruby and some of the work that I did to make it work well. So here's the top line good news. If you look at the building ruby.md document in the source tree, it now has instructions for how to build with address sanitizer. And I can confirm that if you do that, on my machine at least, it compiles and it will pass the test suite if you run make check again on my laptop. This took a bit of doing, and I think some of the bits of this are kind of interesting to go through. So let's have a bit of a look at what needed to change. So the garbage collector needed to learn about ASAN in a couple of ways. So ordinarily, when C functions have access, C functions can hold references in local variables to Ruby objects. We allow that. And the garbage collector will ordinarily find them by just marking the machine stack, like from top to bottom. So let me rephrase that in a different way. Basically, C lays out local variables one after the other in the system stack. And every function's local variables go at the next part of the stack. So they're kind of all laid out contiguously. So all the garbage collector has to do normally is start from the bottom and go to the top and look at every single slot in the stack and be like, okay, this one is not a Ruby value. This one looks like it could be a Ruby object. Let's make sure not to garbage collect that. The problem is, we said before, ASAN doesn't like putting things together like that. It wants to put red zones around everything. So in ASAN, actually, the local variables are not stored on the machine stack at all. When you build a program with ASAN, it actually, every time you enter a function, allocates a special fake stack and puts your local variables for that function there. So that's where all the Ruby references would end up. And if the garbage collector can't see those, then those objects risk being prematurely garbage collected, and all the bad things happen as a result of that. So we had to teach the garbage collector how to find these fake stacks. This is actually pretty straightforward. I think like a really major use case for address sanitizer is browser implementations, because they're all big C++ programs that run unsafe code with JavaScript. So people, they're a big juicy target. And so ASAN has browsers very much in mind. And browsers contain JavaScript VMs. And JavaScript VMs have exactly this problem. They have to find all the references to JavaScript objects on the machine stack. So ASAN has an API that you can use to find out about the fake stacks. And I pretty much just looked at what, not Chrome, Blink. Edge. I looked at the old Microsoft Edge code to find out how they did ASAN marking of GC like this and copied it into C Ruby. And that mostly worked. So that fixed a good part of like the random crashes that I had with building Ruby with ASAN. The other thing to think about is that Ruby has its own idea of what free memory is that's kind of disjoint from the system's idea of what free memory is. So ASAN overrides the malloc and free functions and other memory allocation routines in your program. So it knows when you allocate some Ruby objects and when you allocate some C objects rather, and when you free them. But Ruby's garbage collector kind of maintains its own big blocks of memory, and they're not individually kind of malloced and freed every time a Ruby object is allocated and freed. But it's nice to kind of detect when we write to a free Ruby object that's not actually really free. And poisoning is the mechanism we use for this. So I didn't actually do a lot of this. Many of the kind of required calls to ASAN poison object and ASAN unpoison object were already sprinkled throughout the code base. So I think Samuel had a crack at this beforehand, or maybe some other people had as well. But I was able to add a few missing ones, and then ASAN understands when you try and access a free Ruby object now, because that memory gets marked in the shadow map as invalid, just as if it was invalid according to C's rules. All right, callcc. Many of you may not know what callcc does, or even that it exists. And if that is the case, cover your ears, because you should not find out how it exists. Right? It is terrible, and no one should ever use it for anything, except for trick programs, maybe. It's probably fun there. But it's implemented by calling C setJump and longjump functions from to basically travel back in time, call setJump somewhere, call longjump somewhere else, and then it transports your program back in time, sort of, to how it was beforehand. The manual page for the setJump function on Linux has this to say, which is, if the function which calls setJump returns before longjump is called, the behavior is undefined. Some kind of subtle or unsubtle chaos is sure to result. That is literally exactly how callcc works. It's not a bug, it's the whole implementation. And that kind of subtle or unsubtle chaos, that is exactly what ASAN is designed to prevent. So ASAN rejects programs that use callcc because it's completely invalid according to the C standard. So I kind of looked at whether we could fix that and kind of decided no, and also I don't care. So we just disabled call CC if ASAN is enabled, and that's probably fine for most use cases. All right, for those of you who are blissfully unaware of call CC, you can uncover your ears now. One thing that I thought was going to be a problem that turned out to not really be a problem is existing memory safety bugs. So if you looked at the title of this presentation that was on the agenda, it says, Finding and Fixing Memory Safety Bugs in C with ASAN. Because when I submitted this talk, like 3 or 4 months ago, whenever I had to do that, I kind of thought that running Ruby's test suite with ASAN would shake out a lot of problems that needed to be fixed. That turned out not to be the case. I found 2. I found 2 actual bugs that were the result of like memory issues that ASAN was able to catch. And they were kind of not very serious bugs either. Like if you had an invalid octal literal in your source code, that could cause a buffer overflow sometimes. So like not many people deliberately put invalid octal literals in their code. But I guess I was hoping that this would be, I could have like Peter and Adam's presentation, a pile of PRs on the screen of like all the bugs that this found, but unfortunately, no such luck. All right. What is next? So this is something I kind of wanted to do beforehand, but didn't really get around to it. But it would be good to get ASAN working on Ruby CI. So you can run the test suite with ASAN on my machine. It'd be good if it kept working, because it only works, if it's not tested on CI, there's no guarantee that it keeps working. And hopefully, this will help us catch memory safety bugs as soon as they're committed, rather than having to go through that big loop of people filing bugs and saying, oh, it crashed, and then debugging the bug, and then fixing the bug. It's probably too slow to run ASAN kind of before merging in GitHub Actions, but I think we can kind of run it, nightly or just like after merge on Ruby CI. So I've kind of started investigating how to do that, but haven't. That's coming soon. The other thing is it would be good to get ASAN set up as part of the setup Ruby GitHub action. And I've had some conversations with Benoit about this, so this should be possible. And I've kind of started doing it. But what this would allow, basically, people use GitHub Actions to test their gems against a wide variety of different Ruby versions. So this is the Postgres actions, and it like uses Truffle Ruby and Ruby Head and Ruby 2.5 and make sure that they work in all those configurations. So it'd be good if we could also add, Ruby ASAN to that list. And the reason that would be good is gems with native extensions, like the Postgres gem, for example, might have memory safety bugs in those native extensions. And if they compile with ASAN, then they're going to get the same benefits. So they'll be able to hopefully find memory safety bugs in popular extensions and fix them. So I don't know, maybe after I do that, I can come back with next year with a presentation like Peter and Adam's with all the PRs for all the bugs we fixed. But yeah, so that'll happen soon, I think. But this kind of got me thinking a little bit. ASAN is about enforcing the rules. It's about taking things that are undefined behavior and giving them the very defined behavior of crash. But the LLVM project has lots of other sanitizers in it. So they've got like a thread sanitizer for checking thread safety issues. There's one for checking uninitialized memory. There's one for memory leaks. So it'd be good to, once we wrap up the ASAN stuff, try using some of these as well and see if these turn up interesting things. But then I thought a bit further. ASAN is about enforcing rules, but CRuby has many of its own specific rules that need to be followed when you're writing C code in CRuby, and they're rules around how the Ruby garbage collector operates. So, I was wondering, could we write some sort of ASAN-alike thing that checked for CRuby's rules, like whether you're missing a GC guard that you need, or whether you're using write barriers properly on write-protected objects. This screenshot is a directory from the Chromium source code, and they actually have quite a few custom LLVM plugins. So when you build Chromium with Clang, it can like run custom code to do custom checks on the generated code, on the syntax tree, etc. So I am kind of planning to investigate, can we use compiler plugins to do similar checks in C Ruby? So I think that would be kind of an interesting thing to have a look at. So maybe I'll be here next year with that too. All right. You all came here and listened to this. What do I hope you leave with? I think it's those three things. So if you regularly hack on C Ruby, please try using ASAN in your development flow and throw things at me if it doesn't work. And hopefully we can make that better. And hopefully it can save you some time by catching bugs that would otherwise take a lot longer. If you write native extension gems, consider having a look at using ASAN in your CI pipelines to catch the same sorts of errors in your extensions. And finally, if you work with Ruby, you can try using ASAN to compile your own Rubies, and if you find crashes, you can reproduce those crashes perhaps with the ASAN-enabled Ruby. And that would, at the very least, kind of provide a much better bug report when you go to open your bug to the extension author or to bugs.rubylang.org. Because that'll be much, the ASAN bug report will be much closer to the source of the problem. All right, I talked way too fast and finished too early. But actually, while I have you, there was one thing that I keep getting asked, the relationship between ASAN and Valgrind. So ASAN and Valgrind actually both do very similar things, and they do them in a different way. So ASAN is all about instrumenting the compiled binary. So it changes what's generated, whereas Valgrind is about running on an existing you take a binary that already exists and run it through Valgrind. So it's kind of two different approaches to get the same result. All right, now I'll go away and give you 2 minutes back. Thank you, everyone.